Right now, at opposite ends of the planet, separated by 12,000 miles of open ocean, two ice caps that have behaved like strangers for the entire satellite era are breaking their own records within months of each other. No prior decade in the 7-year satellite record has ever produced back-to-back record low years at both poles simultaneously. No climate model used by the world's major forecasting agencies has consistently reproduced anomalies this large before they happened. This is not two separate weather stories playing out an ocean apart. It is one signal arriving from two different addresses at once. Stay with me, because the last part of this story is something scientists are still actively arguing about in 2026. If you're new here, this channel breaks down what the data actually says about the planet's most extreme systems. No alarmism, no filler. So if that's useful to you, subscribe now. It's free. Let us go back to the beginning. To understand why this moment is strange, you first have to understand why, for decades, scientists expected the two poles to behave completely differently. Sea ice, frozen ocean water, not to be confused with the glaciers and ice sheets sitting on land, forms and melts with the seasons at both ends of the Earth. In the Arctic, that ice floats on an ocean nearly enclosed by continents, insulated from the wider currents of the world's seas. When that ice melts, it exposes dark open water that absorbs far more sunlight than white ice ever would, which warms the ocean further, which melts more ice the following year. This feedback loop is not a new theory. Researchers described it decades before satellites ever confirmed it, and it is one of the most well-established mechanisms in all of climate science. It is why, since consistent satellite monitoring began in 1979, Arctic sea ice has declined in every season, in nearly every year, in a trend so consistent that scientists rarely bother to argue about its cause. It's worth understanding how scientists even measure something as vast and remote as polar sea ice in the first place, because the confidence behind these numbers isn't casual. Since the late 1970s, a continuous chain of satellites carrying passive microwave sensors has been scanning both poles, day and night, through cloud cover and the months-long polar darkness that would blind an ordinary camera. Those sensors detect the different microwave signatures of open ocean water versus frozen sea ice, and the resulting record, nearly 5 decades long now, cross-validated across multiple independent satellite missions and space agencies, is one of the most consistent, most rigorously checked data sets in all of climate science. When NSIDC says a number is the lowest on record, that isn't an estimate pulled from a handful of ship logs. It's built from tens of thousands of satellite passes, compared against every other year going back to 1979. Antarctica was supposed to be different, and for good reason. Antarctic sea ice floats in the open Southern Ocean, exposed to the ferocious, unbroken winds that circle the continent with nothing to slow them down. And for decades, those winds and the southern annular mode, a natural cycle in atmospheric pressure around Antarctica, appeared to dominate the story. Through the entire span of the satellite record from the late 1970s until 2015, Antarctic sea ice extent showed no meaningful long-term decline at all. If anything, it inched upward. In September 2014, it set an all-time record high. Researchers studying the data were clear that this made physical sense. Unlike the Arctic's enclosed basin, Antarctica's sea ice sits at the mercy of a wildly variable ocean atmosphere system, one that could plausibly mask a warming signal for years, even decades, through natural noise alone. That was the consensus. It was reasonable. It was built on 36 years of consistent observation, published in dozens of peer-reviewed papers, and taught in oceanography courses around the world as one of the clearest examples of how two hemispheres can respond differently to the same warming planet. And then, starting in 2016, it started to come apart. Here's the number that matters. In September 2023, Antarctic sea ice reached its winter maximum extent, the point in the year when the ice should be at its largest, and it fell over 2 million square kilometers short of the 1981 to 2010 average. Read that again. 2 million square kilometers of missing ice in a single season on a continent that had shown almost no long-term trend for the previous 36 years. Translate that to something you can actually picture. 2 million square kilometers is roughly 10 times the entire area of the United Kingdom, 10 Britain's worth of ocean that should have frozen over and simply didn't. Researchers at the British Antarctic Survey ran the numbers through one of the world's largest climate model archives, CMIP6, the same collection of models used to write the United Nations' own climate assessments, and found that an anomaly this size was, without accounting for human-driven climate change, roughly a 1 in 2,000 year event. With climate change factored in, it became 4 times more likely, but still almost never something the models themselves managed to produce. The title of the resulting paper says it plainly. The models rarely simulate Antarctic winter sea ice anomalies as large as the one observed in 2023. Sit with that for a second. This wasn't a case of scientists refusing to believe their own instruments. It was the instruments handing scientists a number their own best simulations of the physical world essentially couldn't generate. And 2023 did not stand alone. The following year, September 2024, produced the second lowest winter maximum on record, close enough to 2023's low that NSIDC scientists began openly asking whether Antarctic sea ice had entered what they carefully called a wholly new state. Then, on March 1st, 2025, Antarctic sea ice hit its summer minimum at 1.98 million square kilometers, tying for the second lowest minimum ever recorded. 3 lowest ever winters, 3 lowest ever summers, all within a 7-year stretch on a continent whose entire previous 36 years of data had suggested this kind of behavior shouldn't be possible for centuries, let alone consecutive seasons. This is not chaos. This is a system doing something the historical record has no precedent for. The consequences weren't confined to satellite graphs either. Emperor penguins, which need stable, fast ice attached to the coastline to raise their chicks safely away from predators in open water, suffered what scientists later confirmed as catastrophic breeding failures in multiple colonies during these same low ice years. Chicks too young to have grown waterproof feathers, standing on ice that broke apart and dropped them into the sea months before nature intended. Here's where it gets worse. Those colonies weren't chosen at random by researchers as a worst-case example. They were simply the colonies that happened to be watched closely enough by satellite and by field teams for anyone to notice the failure at all. Nobody knows exactly how many unmonitored colonies experienced the same thing along the thousands of miles of Antarctic coastline. Nobody was watching that particular season. Here is where this stops being abstract. Sea ice floating on open ocean does not, by itself, raise sea levels when it melts. It's already displacing its own weight in water. The same way ice cubes melting in a full glass don't overflow it. But that ice does 2 things that matter enormously to the rest of the planet. First, it acts as a physical buffer, absorbing the pounding of Southern Ocean storm waves before they can reach the floating edges of Antarctica's land-based ice shelves, the shelves that hold back the truly enormous mass of ice sitting on the continent itself. Ice that, if it slides into the ocean, absolutely does raise sea levels by feet, not inches. Strip away the sea ice buffer, and you expose those shelves directly to wave damage they were never built by nature to withstand. Second, both polar ice systems reflect roughly 80 to 90% of incoming sunlight back into space. Lose that reflective shield at both ends of the planet in the same handful of years, and you're not looking at 2 regional weather anomalies. You're looking at a measurable dent in how much of the sun's energy the entire planet bounces away versus absorbs. There's a third connection too, one that has nothing to do with ice sheets or sea level at all. The polar regions help steer the jet stream, the fast-moving river of air that drags weather systems across North America, Europe, and Asia, change the temperature balance between the poles and the mid-latitudes sharply enough, and researchers studying atmospheric circulation have found it can nudge that jet stream into slower, wavier, erratic patterns, the kind linked to prolonged heat waves sitting over one region for weeks, while another gets buried under snow. None of that requires the ice sheets themselves to melt into the sea. It only requires the reflective cap at the top and bottom of the planet to keep shrinking the way it has for the last several years running. Which brings us to the part of this story that plays out less like a graph and more like a thriller, 300 feet under the ice, in one of the most remote places scientists have ever tried to work. West Antarctica's Thwaites Glacier, nicknamed the Doomsday Glacier for a reason that has nothing to do with hyperbole and everything to do with math, is roughly the size of Florida, and it functions as a cork, not decoratively, structurally. Thwaites physically blocks the much larger West Antarctic ice sheet behind it from sliding into the sea, and that ice sheet alone holds enough frozen water to raise global sea levels by more than 10 feet if it were ever fully released. In 2019, a team of researchers aboard the research vessel Nathaniel B. Palmer was sailing in clear water directly in front of Thwaites when, in the span of about 48 hours, a stretch of ice and icebergs 21 miles wide and 15 miles deep simply cracked apart and scattered into the sea around their ship. They woke up surrounded by icebergs the size of aircraft carriers. Nobody predicted that specific event. Everybody on board understood exactly what it meant. The mass of ice that broke apart wasn't the glacier itself. It was a melange, a jammed-together mixture of icebergs and sea ice that had been quietly bracing the glacier's edge, absorbing the pressure of the open ocean so the ice behind it didn't have to. When that brace disappeared in 2 days, it was as if a retaining wall had vanished overnight, with nothing yet known about what would happen to the structure it had been holding back. That uncertainty is exactly why the International Thwaites Glacier Collaboration exists at all, a program built specifically because nobody could answer, with any confidence, how fast this particular glacier might fail. 2 years later, in December 2021, scientists working under the International Thwaites Glacier Collaboration, a joint $25 million research program between the American and British governments, announced they'd found something worse hiding in the data. Deep cracks and fissures spreading through Thwaites' eastern ice shelf, the floating extension that helps pin the glacier in place. Their prediction was specific, and it was frightening in its precision. The shelf, they said, could fracture like a shattered car windshield in as little as 5 years. That warning is now approaching its expiration date. A new study, published in the Journal of Geophysical Research in 2025, went back through 2 decades of satellite imagery, 2002 through 2022, and confirmed the trajectory in exhaustive detail. The total length of fractures around Thwaites' critical shear zone grew from roughly 100 miles to more than 200, the shelf progressively detaching from the underwater pinning point that has helped hold it steady, upstream ice accelerating as its natural anchor loosens its grip. To get direct evidence of what was happening underneath, scientists sent a torpedo-shaped robot named Icefin down to the glacier's grounding line, the exact point where ice lifts off the seafloor and begins to float. Arguably, the single most important and least accessible location on the entire glacier. And confirmed, for the first time with actual visual evidence, that warm ocean water was actively pushing its way underneath the ice itself, melting it from below in a place no human eye had ever seen before. This is not a minor technical footnote. The grounding line is where a glacier decides whether it's still anchored to solid ground or has begun floating free, and watching warm water actively erode that exact boundary on camera is about as close as glaciology gets to catching the crime in progress rather than just measuring the aftermath. Researchers involved in the 6-year collaboration described the overall outlook in their own final report with a single word: grim. Then, just as the data was getting more alarming, the mission to keep collecting it nearly lost its only ship. In May 2025, the U.S. National Science Foundation released a budget proposal that included terminating the lease on the Nathaniel B. Palmer, the same vessel that had been rocked by collapsing icebergs in 2019 and the only research ship in the entire United States capable of reaching Antarctica to study glaciers like Thwaites up close. 170 of them. Researchers signed a letter to Congress and NSF leadership warning that cutting the Palmer loose, with America's replacement icebreaker still a decade from ready, would blind the country to exactly the kind of collapse its own scientists had spent 7 years documenting. The outcome of that fight is still unfolding. What we do know is what happened next. In late December 2025, a crew of nearly 40 researchers left port in New Zealand anyway, headed back toward Thwaites, going in with what one glaciologist bluntly described as a Plan A through Plan F, because at the bottom of the world, in the dead of an Antarctic summer, almost nothing ever goes according to the first plan. Here is what is happening right now in 2026. On March 15th, Arctic sea ice reached its winter maximum extent for the year at 1429 million square kilometers, the second lowest maximum recorded since consistent tracking of that specific metric began in 2006, trailing only the previous year's all-time low. That's right, 2025 set the record, and 2026 came in as the second worst year ever measured, back to back. Meanwhile, the Antarctic side of this story has followed its own unsettling rhythm. The 2025 winter maximum, reached on September 17th of that year at 1781 million square kilometers, landed as the third lowest ever recorded, behind only 2023 and 2024, meaning the 4 most recent years on record now occupy 4 of the lowest positions in Antarctica's entire 47-year satellite history. 2 poles, 2 independent ocean systems, 2 completely different physical mechanisms driving their ice, and both of them producing their worst multi-year stretches on record at the exact same moment in human history. And out past the ice edge itself, aboard a ship that very nearly lost its funding months before departure, that December 2025 expedition to Thwaites is, as this video reaches you, actively deploying instruments through the ice to measure exactly how much closer that glacier's collapse has moved since the last time anyone checked. Consider what that logistics chain actually requires. A 40-person crew, a decades-old icebreaker whose lease was nearly canceled the year before, thousands of miles of open southern ocean between the nearest port and the work site, and a research window measured in weeks before the Antarctic summer closes again, and the ice locks the coastline away from ships for another year. Every data point this expedition brings back has to last the scientific community until the next window opens. There is no popping back down for a follow-up measurement in February. And there is a very specific clock running on all of this. In December 2021, the International Thwaites Glacier Collaboration told the world their best estimate for when the eastern ice shelf could fracture apart, as little as 5 years from that announcement. Do the math, and that window closes this December. December 2026, less than 4 months from the moment this sentence reaches your ears. Nobody, including the scientists who made that call, is claiming they can name the exact day the shelf gives way. Ice sheets don't collapse on schedules the way a rocket launches. But the window itself is not vague anymore. It was given a start date and a length in writing, in a peer-reviewed research program's own public findings, and that clock is now down to its final months, running in real time on a glacier holding back over 10 feet of potential sea level rise. Now, the part of this story that doesn't wrap up neatly because in the actual scientific literature it hasn't. Ask researchers what is really driving the Antarctic sea ice collapse, and you will get two genuinely competing answers, both backed by published, peer-reviewed work. The first, a University of Washington study published in December 2024 found that an arcing pattern of winds circling Antarctica, combined with warm ocean conditions building up to 6 months in advance, could statistically explain about 70% of 2023's record low sea ice. A mechanism specific enough that researchers used it to correctly forecast 2024's low numbers before the season even happened. Under this explanation, what we're watching is an extreme but ultimately natural forecastable swing in ocean and wind patterns, however alarming its scale. The second explanation, laid out in a 2023 study published in Communications, Earth and Environment, points to something structurally different. Substantial warming detected in the subsurface ocean layers beneath the ice during the exact years the record lows occurred, hinting that the entire physical mechanism governing how Antarctic sea ice behaves may have genuinely shifted into something new. Not a temporary swing back toward the old pattern, but a system now operating under different rules than the ones that held for the previous 36 years. What most people are not seeing in the headlines is that these two explanations are not fully reconciled with each other yet, and NSIDC's own senior scientists have said as much in plain language. Whether Antarctic sea ice has entered a genuinely new regime remains an open question. The data alone cannot yet settle. It's entirely possible both explanations are simultaneously true, that unusual but ultimately natural winds and ocean patterns triggered the initial 2023 collapse, while the deeper subsurface ocean warming beneath it represents a slower, separate, climate-driven shift that will keep loading the dice toward extreme lows for years after any single wind pattern fades. Untangling which mechanism is doing how much of the work is exactly the kind of question that takes years of additional observation to answer honestly, not months. Zoom out far enough, and this story stops being about ice at all. It becomes a story about the limits of forecasting any enormously complex system built on decades of relatively stable data. Every model climate scientists use, the same CMIP6 archive that essentially failed to predict 2023's Antarctic collapse, was trained, tested, and refined against a historical record that, for the poles specifically, spans less than 50 years. 50 years sounds substantial to a human life. It is a rounding error to a planet whose ice sheets have existed for millions. What happened at both poles simultaneously in the 2020s is a reminder that even our most sophisticated tools for predicting the future are only as good as the range of behavior they were ever shown in the past. And when a system does something genuinely outside that range, the tools don't fail gracefully. They simply say, correctly and honestly, that what just happened was never supposed to happen this way. That is not a flaw unique to climate science. It's a feature of trying to forecast anything built from millions of interacting variables, whether it's an ocean current, a financial market, or a biological ecosystem. The models work beautifully right, up until reality does something the training data never included. The difference here is that the system in question wraps around the entire planet, and the stakes of being wrong extend to every coastline on Earth. There's a second lesson tucked inside the funding fight over a single research ship, too. The instruments capable of catching a planetary system in the act of changing, a satellite constellation running since 1979, an icebreaker with a standing crew, a torpedo robot rated for the crushing dark beneath an ice shelf, are expensive, unglamorous, and easy to defer in a budget cycle, precisely because they mostly report that nothing catastrophic happened yet. The year that logic fails is the year something catastrophic actually does happen, and by definition, nobody can know in advance which year that will be. Keeping the Palmer at sea wasn't a research nicety. It was the difference between measuring a collapse as it happens and reconstructing one after the fact from whatever evidence survives it. There is an image that outlasts every graph in this story, a 200-foot research ship at anchor in what should have been calm, ice-free water, waking up one morning in 2019 to find itself ringed by icebergs the size of aircraft carriers that had not existed 48 hours earlier. Nobody on board that ship saw it coming in the most literal sense. They went to sleep in open water and woke up inside a maze of ice that had not been there the day before. That is what abrupt change actually looks like when you're standing close enough to it. Not a slow, visible slide, but a system holding its shape until, quite suddenly, over the course of a single restless night, it doesn't anymore. Every chart in this video is, in the end, an attempt to translate that exact feeling. the feeling of falling asleep in open water and waking up surrounded by ice that wasn't there before, into numbers precise enough for a model to trust. Somewhere south of New Zealand right now, another ship is threading its way back toward that same glacier, carrying scientists who know, going in, that whatever plan they wrote before departure will not survive first contact with the ice, because it never does down there, and they are going anyway. So here's everything in one breath. For 36 years, Arctic and Antarctic sea ice behaved like two entirely different systems. The Arctic steadily declining as expected, the Antarctic holding roughly steady or even growing. Starting in 2016 and accelerating sharply by 2023, that pattern broke, with Antarctica posting its 3 lowest winters and lowest summers on record within a single 7-year stretch, and anomaly climate models built from decades of data essentially could not reproduce. At the same time, the Arctic posted its lowest ever winter maximum in 2025, followed immediately by the second lowest ever in 2026. Beneath West Antarctica, the Thwaites Glacier's eastern ice shelf has been fracturing on a 5-year clock set in 2221 that closes this December, even as the one ship capable of monitoring it nearly lost its funding entirely. And whether the Antarctic collapse reflects a temporary forecastable weather pattern or a genuine permanent shift into a new physical regime is a question researchers have not yet fully answered. If you want to know what that ship finds when it reaches Thwaites, or what happens when that 5-year window closes this December, subscribe and turn notifications on, because I'll be covering both the moment there's real data to report. Here's the question I actually want your answer to. Given everything you just heard, do you think what's happening at the poles right now is mostly a wild natural swing the planet has survived before, or something genuinely new? Tell me which one and why in the comments. I read every single one.